consider the following two equation statements. Sine of x is half, or sine inverse of half is x. Are they equivalent? Yes. If you'll remember, if I'm finding sine of an angle, that gives me a leg, right? And more specifically, it gives me a vertical leg. We've talked about that. That's the y piece. Yeah. Okay. If I take sine inverse of a leg length, I am finding an angle. Okay, so that's a quick recap of how inverse works. Any questions there? Okay. So are these two equations equivalent? Sure. On the unit circle, we know there are two angles between 0 and 2 pi, where sine of theta is half. That happens at pi over 6 and at 5 pi over 6. However, due to the domain restrictions, we would say only pi over 6. Okay? As a result, when we're solving equations involving trig functions, we must modify our solutions to account for those domain restrictions. And we did that. We did that yesterday. Or the lack of any domain restrictions. That's where we are today. It says finding general solutions to a trigonometric equation. So this is going to be halfway down the page. Since trigonometric functions are periodic, we can have infinitely many solutions to an equation if no domain restrictions are given. So let's consider equation 1 from above. We know that sine of x is half when x equals pi over 6 and when x equals 5 pi over 6. Are y'all reading that? Mm-hmm. However, since sine is periodic with a period of 2 pi, we also know that sine of x is half when x equals pi over 6 plus 2 pi, which would be at 13 pi over 6. Or let's say I make 2 trips around the circle. Then what? Okay, so you should just be able to add 2 pi to your 13 pi over 6, right? Plus 2 more pi, plus 2 more pi. And you could tell that that's happening every trip around the circle. It's hitting that mark again. Do you understand what I'm saying here? Okay. In fact, we could keep rotating around the circle as many times as we want to. So in order to handle that, we write our answers in this form. We know that this happens, sine of x is half, when x is 5 pi over 6 plus 2 pi k, where k is any integer. And also, x equals sine of 5 pi over 6 plus 2 pi k. That handles both clicks. One on the left, one on the right. Does that make sense? Girls, do y'all have questions? No? So, cosine x equals half. Let's look at this one. When does cosine x equal half? So that's meaning cosine is a short. Cosine is a short. So a short in x means a tall function, right? Pi over 3. Good. Pi over 3. And also?
2 pi over 3.
No, cosine's positive half. Down here, quadrant 4. Tricked you. Sorry. Pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3. 5 pi over 3. So the restrictions are out the window, but we're going to say this could repeat infinitely many times. So we've got pi over 3 plus 2 pi k and 5 pi over 3 plus 2 pi k. Cool beans? Okay. Tangent, it's the same idea, except the period of tangent is pi. So it's just pi k. This is how nerdy things happen to me. Are y'all ready for this? I got invited to a Pi Day Pi K. Oh. Like a 5K, like a running event, but it's on Pi Day, which is March 14th. And it's Pi K. It's a kilometer. Yeah, 3.14 kilometers instead of 5 kilometers. Yeah, it came up in my email. I got an invitation to a Pi Day Pi K.
Are you going to go do it?
No, I'm not going to do it. But y'all need to know, like, it happened to me. It could happen to you, too. Y'all could be nerds. Pi day, pi k. I might do it just for the t-shirt.
Do.
If I get the t-shirt, y'all can't make fun of me. I will wear it.
I'll give you $5.
I will wear it. Pi day, pi k. Do you know what the price is for the entrance? Y'all think?
$3.14.
It's 30.14, but yeah.
For
the entrance fee.
31.
Registration fee.
Miss Armenta, I will give you $30 to go run.
Just to go, yeah, we could raise it. Then I could have a shirt. Y'all could raise money and I could have a shirt. This would be great. All right, let's go on to example 1. Example 1, it says, find all the solutions to the equation cosine x equals negative square root 2 over 2. Okay, so negative, so where are we?
This side.
Yeah, we're in quadrants 2 or 3. Okay. We've got leg lengths of square root 2 over 2. We've got to be at a 4, right? At a pi over 4 of some sort. Well, that's going to happen here and here. This one's going to be negative, or 3 pi over 4 or 5 pi over 4. Happens both times, right? So we have two solutions. X equals 3 pi over 4 plus 2 pi k. I did not sign up for a 2 pi k. I would have only signed up for a pi k. How far is a 2 pi k, Kim? Say 6 kilometers.
How much
Nobody
is
wants
6
to.
kilometers in miles?
What?
I don't. What is a kilometer?
Okay, so you got two solutions here. 3 pi over 4 plus 2 pi k, or 5 pi over 4 plus 2 pi k. Questions? Everybody good? Okay. I told you, I feel like this is a little easier. Do you have to write on both? Yes. It happens both times.
There's only one on example 2.
Okay, find all solutions to the equation sine x equals negative 1.
At the bottom.
At the bottom, when? 3 pi over 2 plus 2 pi k. It only happens once, true, it said. Only one time, true. True that. Good job. Okay, example 3. Find all the solutions for tangent x equals 1 over square root 3. What I know about this is my square root 3 is in the bottom. So this is going to happen when cosine has a square root 3 in it. Can you see that? So if I'm really thinking sine over cosine, I'm going to have a half and a square root 3 over 2. So at what angle does that occur? That sine is a short and cosine's a long.
Oh, your pi over 6.
That's your pi over 6s. Good. So those, find all solutions. Now we need positive. Positive pi over 6. Tangent's going to go positive, negative, right? Tangent repeats itself every pi. So we're at pi over 6. Should I mention the 7 pi over 6?
No.
Okay, so let's say this. X is equal to pi over 6 plus pi k, because tangent's period's pi. Doesn't that handle the 7 pi over 6?
Yeah.
It catches the next one. Tangent's period is only pi. So I don't have to mention both within a 2 pi period. I'm only going to catch the top half on tangent.
Oh, I guess they're both on the same side.
That's what I'm saying. Okay, so we understand that it happens again right here, but we say that by saying it repeats again in pi. What's pi over 6 plus pi? 7 pi over 6. Boom, you hit it.
Wait, tangents, this is your restriction.
No restrictions here. We're throwing restrictions out. We're saying tangent's period is pi. So it's going to catch the repeating right here.
Because if you add 6 pi over 6, you're going to be at
7 pi over 6. Exactly. Now you're there. Good. Okay, this is cool. Everybody repeat. This is cool.
This is cool.
Berlin, looking at you. This is cool. She says with all the sarcasm ever. Okay, I like these though. I really do. We're solving here. So we've got some equation, 6 sine theta equals 3 square root 2. We want to isolate the trig function first. Isolate the trig function first. So the first move we're going to make here is to do what?
Square root 2.
Divide by 6 on both sides. Divide by 6 on both sides. So what's left? Sine theta is equal to 3 square root 2 over 6, also known as square root 2 over 2. So sine theta is square root 2 over 2. When? Good. At theta equals pi over 4 plus 2 pi k. When else? And 3 pi over 4. Theta equals 3 pi over 4 plus 2 pi k. Good. So what we did there was we said it happens at positive pi over 4. That sign is up, positive square root 2 over 2. That happens again at 3 pi over 4. That sign is positive square root 2 over 2. Why not 5 pi over 4? That would have been negative square root 2 over 2. Right? Same thing for 7 pi over 4. No good. This is negative square root 2 over 2. Questions there? Hello? Do you have the questions? No.
Is it 0?
Okay. We'll go on. Example 5 says, let f of x be this thingy, and let g of x equal 2. In the xy plane, what are the x coordinates of the points of intersection? So what are we going to do here? Set them equal to each other. They're points of intersection. Set them equal to each other. Points of intersection of the graph of f and g. So we're going to set f equal to g. We've got 3 plus 2 cosine x equal to 2. And we want to solve. You got to iso the trig function. What's my first move? Minus 3. Good. So 2 cosine x equals negative 1. And then? So I'm dealing with the equation that says cosine of x is negative 1/2. If I solve for x, that looks like x equals cosine inverse of negative 1/2. Just wanted to show you that move. We don't divide by cosine. We cosine inverse on the other side. Okay, so the question here is, when is cosine a negative half? So cosine is a negative short. That means I'm in quadrants 2 and 3. Cosine's a negative short means I have a tall angle, a pi over 6 in quadrant 2. A pi over 3 in quadrant 2. 2 pi over 3 and 3 pi over 3, 4 pi over 3. Good. So x is equal to 2 pi over 3 plus 2 pi k. Oh, look. Grace knows things. Look at here. Only on the interval from 0 to 2 pi. So we actually don't have to say this part about plus 2 pi k. X equals 2 pi over 3 and x equals 4 pi over 3.
You said 3 plus 2 cosine x equals 2.
Because we set f and g equal to one another.
You solved for it.
Yeah, because we needed points of intersection for f and g. Okay, so that comes from reading really carefully here. On example 5, they said only on this interval from 0 to 2 pi. So now I don't have to say the repeating function business. Are we clear on that? Say it again. No, we threw out restrictions on inverses. That was the first thing that we did today. It says all of them. Where are the x coordinates? All of them. Okay, good question. All right, here we go. When we want to square trig functions, this gets interesting. Okay, this is a notation thing. It says when we want to square trig functions or raise them to any exponent, we do not want our notation to be overcomplicated or ambiguous. If we want to square the variable x, we write x squared. But trig functions would create a bit of an issue if we did that. Okay, if we wanted to square the expression sine x, we must be really clear to communicate our intentions. If we write sine of x squared, it looks like I'm squaring the argument, x squared. Do you see the problem with that? Everybody look. Look right here. If we write sine of x squared, then it looks like we're only squaring the variable x. So we need to square the entire expression. We could put parentheses. We could write it like this, sine x squared. The more conventional notation and what we usually do in class is we'll write it as sine squared x. This is saying sine x squared, but I know that I'm trying to square the sine, the operation, the trig value. So when you see this business, you need to know that's sine squared. Sine squared. It's a convention. And we drop that squared in between so I know for sure I'm not squaring the argument. I'm squaring the sine function. Okay? This is yes. Okay, so let's work with that. It says the function g is given by g of x equals 3 minus 4 sine squared x. What are these zeros? How do I find zeros? Set it equal to 0 and solve. We're looking for all of the places where g of x equals 0. So we're going to take our g of x sentence. You're not going to want to miss this. Wake up. 0 equals 3 minus 4 sine squared x, and we're going to solve for x. So what's my first move? Move the 3. Negative 3 equals negative 4 sine squared x, and then divide by negative 4. It's killing me to have my letters on the other side, so I'm flipping right now. Sine squared x equals 3/4. Well, I don't recognize that from my unit circle. 3/4. That never happens. It's squared. So how do I undo squared? Square root. I can square root both sides. And now sine x is equal to square root of 3 over square root of 4, which is square root of 3 over 2. Did y'all catch that? When I square root a quotient, I square root the top and the bottom. So when is x... What's x equals sine inverse of square root 3 over 2? Where's sine square root 3 over 2? Where? Is it tall? Pi over 3, good. 2 pi over 3, very nice. We're on the interval from 0 to 2 pi, so we don't have to keep repeating. Okay, so these are talls. X is going to equal pi over 3. And 2 pi over 3.
Is there a reason we don't have to say plus or minus? Let's go with it. Did you not count something?
You should. Great question. He said, is there a reason we didn't count plus or minus on the square root? We should count them. So now we're going to handle all of the pi over the 3 square root 3 over 2s. The positive ones, which we just did, and the negative ones. So we got pi over 3. I'm going to erase so I have more room. Pi over 3. 2 pi over 3. What else? 3 pi over 3. 4 pi over 3. And 5 pi over 3. Yay, Nikki. You should count them all. When we square root, we have the positive and the negative options. I think I missed that when I did this the first time as well. I think I wrote on my paper, it says, whoa, watch the plus and the minus. I got them. I just missed them twice in a row. It's fine. Y'all got 2 more examples in you?
Yeah.
Can you do it?
Yeah.
Do we need to stand up and stretch first? Watch, I'm going to pause. We're going to stand up and stretch. Oh, yeah, we are, and we're singing too. Okay, I feel better. Example 7. We got only 2 examples left, y'all. We can do this. What are all the values of theta between 0 and 2 pi where cosine squared equals negative cosine theta? There's a reason I woke you up for this. This is going to be great. Cosine squared equals negative cosine theta. Here's what I'm thinking. You have got to remember that if I had x squared equaled negative x, you can't divide by x on both sides or do some weird business. If you're dealing with a quadratic equation and you're trying to solve, your move is set it equal to 0 and then factor it. You need to set it equal to 0. So we're going to add x to both sides here. And I would have x squared plus x equals 0. And I would factor out in, and I would be left with
x plus,
and I would solve both, right? I would have x equals 0 and x equals negative 1. We have to treat the trig the same way. Okay, so we're not able to look at this cosine squared theta equals negative cosine theta and do anything but this. It's quadratic in every way. And we're not able to sit here and look at it and say, hey, I'm going to divide by cosine or do something weird that would get me out of the shape that we're in here. Our move is swing the cosine. They are not like terms. I don't get to combine them. One's squared, one's not. I wouldn't ever think to combine x squared with x, right? You would not do that. You know better. You cannot combine cosine squared with cosine. So we're going to swing this cosine to the other side. We're going to have cosine squared theta plus cosine theta equals 0. Both terms have a
cosine theta.
So we should
factor
out cosine theta. Welcome back, Truett. Stretching was good for you.
I've been here the whole time.
You have not. Cosine theta plus what's left in the second term? 1 equals 0. And now we set each
equal to 0.
And?
Solve.
Okay.
0 and negative 1.
So cosine theta equals 0. Also, cosine theta equals negative 1. You swung that 1 already? Are y'all good with that?
Yeah.
So we should be coming up with two solutions here. Cosine theta equals 0. When? Pi over 2 and 3 pi over 2. Nice. Cosine theta equals 0 at pi over 2 and 3 pi over 2.
And then equals negative 1
at
pi.
Cosine theta equals negative 1 when theta is pi. We're swinging to the left right there. Solid?
Yeah.
Cosine theta equals negative 1. That means I have a negative x. Negative 1 in x. That's going to be on the right side at pi. Left side. My right, your left. Yeah?
Mm-hmm.
So these are my three solutions. Pi over 2, 3 pi over 2, and pi. Yes. Okay. Last one. Let f of x equal 2 sine squared x and g of x equals square root 3 sine x. In the xy plane, what are the x coordinates of the points of intersection, again, for f and g? So we're going to set f equal to g. I don't know who missed that earlier, but that's what we do when it says points of intersection for f and g. Set them equal to one another. So we've got 2 sine squared x equal to square root 3 sine x. Now what? Swing it over. Set it equal to 0. Factor. Okay? Swing it over. Guys, resist the urge to do anything but that here. Swing the sine x. You can't divide that out.
But now you have a minus square root 3.
Okay.
That's dumb.
So we're going to have 2 sine squared x minus square root 3 sine x equal to 0. And now both have a sine, so we can factor it out. So we'll have sine on the outside, sine x. What's left on the inside? 2 sine x minus square root 3 equals 0. I've got two factors equal to 0. The zero product property says if the product of two factors is 0, then either one or both of them was 0. Right? So we set each equal to 0 and go from there. So when is sine of x equal to 0? When x equals
Pi over 2. No. Pi and 2 pi.
0 and pi and 2 pi and 0 and pi and 2 pi, right? Well, look on our interval. We're from 0 to 2 pi. We include 0 because it says 0 is less than or equal to theta. So x equals 0. X equals pi, not 2 pi. Why not?
It doesn't have the line.
Because it doesn't have the line. It's not or equal to. So 0 and pi. That'll catch both of those. We've got one other equation. 2 sine x minus square root 3. 2 sine x minus square root 3 equals 0. Swing the square root 3. 2 sine x equals square root 3. Divide by 2. Sine x equals square root 3 over 2. So x must be, these are talls, right? Pi over 3 and 2 pi over 3. Pi over 3 and 2 pi over 3. So this one had 4 solutions actually. 0, pi, pi over 3, and 2 pi over 3. Easy, he says. Easy. Good. Any questions on that, y'all? You have homework tonight. Homework. I think let's check all 3 worksheets by Friday. 3.8, 3.9, 3.10, part 1. Check them by Friday.